Hi, I'm Mr. Gherkin. Welcome to physics. We are going to be learning about harmonics today. Let's look at an example.
Oh, I didn't see you there. Hey, it's me, the Gherk. I was just learning how to play the trombone because it's a good way to demonstrate the principle of harmonics. Here, let me show you. Can anyone tell me how I kept the same position but played two different notes?
Magic.
No, you idiot.
Mr. Kirkin would never say that.
I'm just kidding, Jacob. It's because of physics.
Wow.
Certain mediums, such as the length of a tube or a string, for instance, have a certain length of waves that fit inside it comfortably. However, there are other lengths that also fit inside the medium. This means that any note has other frequencies that can resonate along with it.
This phone app shows the frequencies that it hears. The leftmost spike is the fundamental frequency. It is the simplest possible wave that fits comfortably in the trombone. The other subsequent spikes represent the harmonic frequencies. They are more complex frequencies that also fit inside the trombone.
What?
It's okay, Jacob. To make this clear, we're going to look at what's going on inside a trombone.
I still don't see anything, Mr. Gherkin.
Where'd you even get that?
Hello, my name is Mr. Gherkalicious, and here we have a drawing of a tube. Now I'm going to draw the simplest wave that can fit inside this tube. This is the fundamental harmonic. The next wave that can fit inside this tube has another node-antinode pair. This is the second harmonic. We can add more nodes and antinode pairs to make it more complex.
But what if the tube has closed ends?
Excellent question, Jacob. This is what the fundamental frequency looks like with closed ends. Now we're going to look at some equations.
Hello! It is I, Mr. Gherkin, Esteban Julio Ricardo Montoya de la Rosa Ramirez, and I am here to show you some equations. Here we have the diagrams of an open and closed tube. So we're going to set the length of the tube equal to L. Now, for the fundamental harmonic, notice how in this tube there is 1/2 of a wavelength inside the tube. It goes from this point on the top to this point on the bottom, which is 1/2 of this wave. The same goes for this one, only it starts here and ends here. So we're going to write this as 1/2 times lambda is equal to L. Now for the second harmonic, we see that it goes from the top all the way back up to the top, which is 1 full wavelength. And for this tube, it goes from this point to this point. So we are going to write this as 2 over 2 lambda equals L. So we can continue to do the same thing for the other tubes until we end up with 3 over 2 lambda equals L and 4 over 2 lambda equals L. So actually we can notice a trend here, because if the number of the harmonic is equal to n, for example this would be n equals 2, n equals 3, n equals 4, we can write the equation as n over 2 lambda equals L, or lambda equals 2L over n.
But wait! What if one of the ends is open and one of the ends is closed?
Excellent question.
This is the simplest wave that can exist in a tube where one end is closed and one end is open. So this is our fundamental harmonic, and these are the subsequent harmonics. However, this means that the equations are different from the equations we found before. This tube is a quarter of the length of a wave. This is 3/4, 5/4, and 7/4. Now, according to the definition of a harmonic, the wavelength of the nth harmonic must be equal to the wavelength of the fundamental divided by n. However, according to this definition, the second tube should have a wavelength that is 1/2 that of the first. But it's not. It's 1/3. This means that on a tube that has one closed end and one open end, there can only be odd-numbered harmonics. So our equation turns out to be lambda equals 4L divided by n, where n is odd.
Hello everyone, I am Mr. Barkin. We are going to use the equations to find the length of a tube that will make a particular frequency resonate.
Up at the top of the board, we have our givens. Using our definition of frequency, we can plug in the values of f and v to solve for lambda. This gives us 0.773 meters for lambda. Next, we rearrange the equation for wavelength to solve for L. The first value of n we will try is 1, because we are looking for the fundamental frequency. Using this equation, we find that L is equal to 0.193 meters, or 19.3 centimeters. This means we need a 19.3 centimeter long tube to make a 440 Hz tuning fork resonate.
Oh, good.
Thank you very much for learning with us today. We enjoyed learning with you.
Jacob.
Gurkalicious.
This definition make them boys go loco. They want my treasures so they get their pleasures from my photo. You can see me, you can't squeeze me. I ain't easy, I ain't sleazy. I got reasons why I tease them. Boys just come and go like seasons.
Gurkalicious.